Greetings, physics enthusiasts. Welcome to AP Physics 1, Unit 6, Lesson 4, where we are going to continue thinking about simple harmonic motion. So simple harmonic motion is the back and forth motion that a simple harmonic oscillator has. So, and there's a couple different ways of thinking about that. We could have a block attached to a spring, and if this is L naught, the natural length of the spring, then the block would sit here at rest and remain at rest forever, because the net force acting on the block is 0. However, if I were to displace the block from equilibrium, I'm wearing my computer glasses and I can't see. If I were to displace the block, what if I pull the block out to the right? And I'm just going to hold it here so everybody's at rest. And I let go. Well, the block starts at rest and it speeds up as it approaches equilibrium. When it gets to equilibrium, it's got its fastest speed, and it slows down and stops because the spring pushes it and stops it. So as the block goes back and forth, the block is a simple harmonic oscillator, and the block has or experiences or demonstrates simple harmonic motion. Okie dokie. Now, another way we can think about this, though, is we could draw a circle underneath here. Let's pretend that's a circle with a center. And as a dot moves around the circle at constant speed, in other words, in uniform circular motion, where the speed is always constant, the horizontal component of that speed would correspond exactly with the back and forth simple harmonic motion of this block. Similarly, if I had a hanging block that was hanging here and then I moved it up here, the up and down motion of that spring would perfectly coincide with the vertical component of this uniform circular motion. So simple harmonic motion can be thought of as either the horizontal or the vertical component of uniform circular motion. So they are very, very closely related. And we've talked about that before. What I'd like to do today is look at some of the math. Yay, because math is fun. So thinking mathematically. Thinking mathematically now about this, we could call, let me label these locations. I'm going to call this location 3, and this location 2, and this location 1, and 4, and 5. So this distance from equilibrium to all the way out is the amplitude, and this distance from equilibrium all the way out to the other end is also the amplitude. And let's just think about the energy that this system has. I pull the block out over here and I'm holding it. While I'm holding it, is there any energy in the system? And the answer is yes, there is. I have stretched the spring, stretched the spring, stretched the spring. So I have stored energy in the spring. And I could write 1/2 kx squared, and that's the energy stored in a spring stretched a distance x. Well, here the spring was not stretched at all. Here it's stretched more, the most, less, not stretched, stretched more the other direction, more, the most, less. Now, first of all, these are positive displacements to the right. These are negative displacements to the left. That doesn't matter because positive or negative values are, each of them is going to get squared, and I'll end up with a positive value here. But the other thing I'm going to say is I'm going to have this be the initial energy. So I'm going to write A here. I start out with an energy equal to 1/2 k a squared. Why did I not write plus 1/2 m v squared? Because at the beginning, the speed is 0. We're over here, speed of 0, ready, set, go. The speed is 0 when I let go. And the displacement is A. So this is a very specific initial condition when the speed is 0 and the amplitude is A. At the end, well, I don't know when the end is. Is the end here or here or here or here or here or here? The end is any moment that I want to ask you a question about. So at the end, I have some speed, v final squared, and we're at some location, 1/2 k x final squared. So there is any location along here, x, x is a big number, x is less, 0, x is a bigger number all the way up to a. And as you can see, when x is smaller, v is going to be bigger. When v is smaller, x is going to be bigger. But this equation, given the initial amount of stretch that you have on the spring, maybe if I do it this way, you can see it better. Given the initial amount of stretch, A, at any location, you can tell me the speed, or for any given speed, you can tell me where we're going to have that speed. So this is a very helpful equation. Now, there's an equation in the book that just solves this for V. So what would happen if I wanted to solve for V? Well, I could multiply both sides by 2, and all those 1/2 would go away. And then I could take this and put it on the other side, and then I could divide by m and take the square root. So again, let's talk about that algebra. I'm going to get rid of the 1/2 because they're in every term. If I want to solve for V, I'm going to take this term and move it over to this side and make it negative. And then if I want to isolate V, I'm going to divide by m and then take the square root. So V final equals, now when I take the square root of both sides, I need a plus or minus. You learned that in your math class. The square root of, and then we had an over m, everything over m. And then what I had was ka squared minus kx squared. Ka squared minus kx squared. Yes? Now, it doesn't look quite like that in your textbook. So let's massage this. Let's change it a little bit to get it to look like it does in the book. Do you see that there's a ka squared minus kx squared? There's a k in each term, so I can factor out that k. And then I have k over m, k in the numerator, m in the denominator. And then I have a squared minus x squared. And I think that's how the equation looks in your book. How do you find the speed at some location? Well, it's going to be plus or minus k over m, a squared minus x squared. A being the maximum displacement and x being whichever location you're interested in. Why plus or minus? What about when you're right here? Well, sometimes the block goes by to the right, and then it goes by and it's going to the left. And then it goes by that dot again going to the right, and then it goes by that dot again going to the left. So when we're at this location, we might be traveling to the right, we might be traveling to the left. Is that right and left for you? I can never remember how Zoom and YouTube and Edpuzzle flip me back and forth. Anyway, but I know this is right for you and this is left for you. So sometimes you're going by to the right and sometimes you're going by to the left. So great equations. And this one leads to this one. Let's think a little bit more mathematically about this back and forth motion, remembering that this back and forth motion has to do with circular motion. Let's say we're right here. And the velocity looks like this. And my location right here, x. Do you see that my location along here, this block's left-right location has to do with this angle. And in fact, this distance is, I might want to call this R for the radius, but do you see that the radius is also A, the amplitude? Do you see that this horizontal distance is a cosine of theta? So as we go around the circle, the horizontal part of our motion is A times the cosine of the angle, which changes at constant rate. So let's look at that over here. Let's make a graph of X versus T, position versus time. Now, the position is on the vertical axis because we want time on the horizontal axis. So even though my oscillator is moving back and forth horizontally, I'm plotting position on the vertical axis. So the farthest we're going to go away from equilibrium is A, and then we're going to go that same distance, negative A, on the other side. So this would be a displacement of A, displacement of 0, displacement of negative A. And we see that the position as time changes goes back and forth with this cosine graph. Let's see if we can make that make sense. This is what a cosine graph looks like. Not the best drawing in the world, but it has the important parts. So as this goes back and forth between what I'll call equilibrium and A, the amplitude, and A, the amplitude on the other side. This picture corresponds to me pulling this thing over to the right and letting go. On your mark, get set, go. Where are we when T equals 0? When T is 0, we're at a location A. And then as time goes by, we get back to equilibrium, and then we go over here to negative A. And then we get back to equilibrium, and then we get over here to positive A. So this graph, going from the beginning to here, one complete cycle on the graph, corresponds to starting here, on your mark, get set, go. I let go, and it goes back and forth. And so one of the reasons that I'm having you focus on this cosine is this is the way we usually think of it. We usually think of pulling the block out to the right, on your mark, get set, go. The cosine graph corresponds to that. Could I, in another color right underneath here, graph velocity as a function of time? Yes, I could. Now, if you want a challenge, press pause right now and see what you can do with the velocity versus time graph, and then I'll show you. So the velocity versus time graph, it turns out at the beginning, on your mark, get set, go. What's the velocity at the beginning? It's 0. And then we go over here, faster, faster, fastest, slow down, stop. Faster, 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 fastest, slow down, stop. So am I going to the right or to the left at the beginning? I'm traveling to the left. So if I'm traveling to the left, my velocity is negative. Faster, 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 fastest. So I want my velocity to look like, by the time I get to the center here, I want to have gotten to my greatest velocity, my greatest negative velocity. And then I slow down, stop. That looks like this. Velocity graph, farther from 0, closer to 0. This is speeding up fastest, slowing down, stopping. And so this vertical line, we get back to the origin when we're going the fastest. And then this, we're far away when we stop. And then by the time I get here, back to the beginning, I should have sped up going forward and then slowed down. So maybe the left-right size isn't perfect, but The position versus time graph looks like a cosine. And then if you paid attention during the trig lessons in your math class, you're thinking, well, this sort of looks like a sine, but sine went this way. So this was a cosine graph. This is a negative sine graph. Just, match it up to what you remember from your trigonometry lessons. If you have taken calculus, you might notice that the derivative of cosine is in fact minus sine. And that's a fun thing to notice. Not the big part of the lesson because not everyone has to have taken calculus, but if you have taken calculus, that should make you happy. All right, let's look at one more thing mathematically. In general, the position graph this is the position graph. Now, a regular cosine has a height or an amplitude of 1, but it's not always the case when I have a block that I pull it 1 meter to the right before I start. So this amplitude is A, and I can make that happen in front of the cosine graph if I just write the letter A. So that's taken an amplitude of 1 that was implied before the cosine and turned it into A. And I can make that amplitude bigger or smaller. So A can be greater than or less than 1, however many meters to the right I pull that block before I let go. Now, what's going to go inside the cosine? The argument, as we call it. Now, I showed you that we had an angle here. Yes. And if you remember, rate times time equals distance, or VT equals X, right? We can also talk about rate times time equals distance in terms of rotational motion. So I can write rotational velocity times time equals rotational displacement. So instead of theta here, I can write omega t. And that's exactly what I'm going to do. I'm going to write omega t right there. And that is our general equation, A cos omega t. Not just for the circular motion, but also for the back and forth motion. Because remember, this back and forth motion is just the horizontal component of the circular motion. So this is our general starting equation, A cosine omega t. Pardon me. Now, the velocity graph, if you're in calculus, this is just for the calculus people. If you're not in calculus, it's okay. Save this for later, and it'll sound familiar when you learn this. But the derivative of a constant times a function is the constant times the derivative of the function. And the derivative of cosine is minus sine of omega t. And don't worry, I know the chain rule. Some of you are like, wait, don't forget the chain rule. So the derivative of a function within a function is the derivative of the outside, which we already did, times the derivative of the inside. The derivative of omega t with respect to t is omega. So I have to multiply by omega. And so this equation is in your textbook, and that's where it came from. Hey, let's talk about acceleration. We've talked about acceleration being the derivative of velocity. So here I've got my constant minus a omega, and then I'm going to multiply. No, I'm going to take the derivative of sine, which is cosine. The derivative of the sine is the cosine. But wait, I have to do the chain rule. The derivative of omega t again is omega. So I have to multiply by another omega, and I get an omega squared there. So these three equations are very helpful for us. The back and forth motion, here's the position as a function of time, here's the velocity as a function of time and the acceleration as a function of time. And all of those correspond to the situation where I pull the block to the right, over to the right, to begin things. And I start all the way over here at an amplitude a to the right, and I let go. And my original speed is 0. Why is the original speed 0? T equals 0. Omega times 0 is 0. What's the sign of 0? 0. T equals 0. What's omega times 0? 0. What's the cosine of 0? 1. So my original position is 1 times a, or just a. Yay. So it all makes sense. Thinking about this mathematically. Now, there's one more thing I want to tell you. I'm not going to derive this for you here today, but it can be derived and you can look it up. Omega. I'm going to give you a formula here that's really going to be useful for this omega and this omega and this omega. Omega is equal to the square root of k over m. K over m. That same k over m that came from over here, the angular frequency. This is called the angular frequency. And what I have found in my 30 years of physics teaching is that one of the hardest things for students is to remember, is it k over m or m over k? So first of all, I'm telling you it's k over m, so maybe you just want to memorize it. But think about an oscillator going back and forth. Maybe for some reason it's going really slowly with a smaller omega. Why would that be? One thing that could make omega really small is if you stuck something really massive here, like a bowling ball, would not go back and forth super fast. Or maybe it's because, so big M or small k, like a slinky, would not make a ball go back and forth very fast. So either small k or big M, kind of gut-wise, intuitively feels like a small angular frequency. Whereas a really stiff spring would make things go back faster, would make a larger frequency. Or putting a smaller, like just a little, what do you call those little ball, marbles, put a little marble on, and it would be able to go back and forth a lot faster than a bowling ball. So think about your gut intuition. It makes sense for k to be in the numerator and m to be in the denominator. So let's talk about the kind of problems that we deal with. Sometimes a problem will say, hey, there's an oscillator, and here's the equation that governs its motion. X equals 36 sine 3t. What do you know if x equals 36 sine 3t? Well, first of all, I know that a equals 36. So anyway, this is what's given. What do we know? I know that a equals 36. So it goes 36 meters to the right before it starts. And we'll actually, not necessarily, sine. We're used to x being a cosine graph. Sine, oh my goodness, when t equals 0, 3 times 0 is 0. What's the sign of 0? 0. In other words, if there's a sine here instead of a cosine, it means that the block actually started off in the center at equilibrium, not over here at A or over here at A. Can that happen? Sure, maybe there's a block there and I hit it with a hammer. That would make sense. Sine, so if this is my x versus t, it looks like a sine graph, not a cosine graph. So it moves to the right and then back to 0. And then it moves to the left and then back to 0. So this sine tells me it starts in the center and I hit it with a hammer to the right. This 36 tells me that it goes all the way over here and that this distance is 36 meters. It also tells me that this distance is 36 meters. So on your mark, get set, go. It starts in the center. I hit it with a hammer and it's going really fast. Goes to the right and stops, comes back. Goes to the left and stops and comes back. Do I know anything else? Do I know anything about how fast it goes or how many oscillations it makes every second? Well, this 3 is equal to omega. So I know omega equals 3. Now remember, we said omega was also equal to 2 pi f. Does that sound familiar from a previous lecture? It should. So what that means is that the angular frequency is 3, or the frequency is 3 over 2 pi. Let's just stick that into the calculator really fast and see what kind of number we're talking about. 3 divided by 2 divided by pi, and I get 0.477. Did you see how I did that? I divided 3 by 2 pi. I'm tempted just to call that 1/2, but we'll call it 0.48, which is about into 0.48. So I do almost a half of a cycle each second. Frequency has the unit s to the -1. So I go almost all the way over and back in a second. Maybe not quite. All the way over, almost all the way back in 1 second. So it takes 0.48, almost half in a second, almost half again in a second. So it takes a little more than 2 seconds to go all the way. Because remember, the period is 1 over the frequency. So I had 3 divided by 2 divided by 3.14. And then I'm going to take the reciprocal of that, 2.09. We'll call that 2.1. The period is 2.1 seconds. 1/1000 to 1,000, and then another 1/10 of a second. So I know the period, I know the frequency, I know the angular frequency. Isn't that nice? Notice that frequency and angular frequency each have the same unit. They're both s to the -1, because all I do to the frequency is multiply by 2 pi, no unit, to turn it into angular frequency. I could also find the speed at any given time using this, right? Because now I know A is still 36, omega is 3, and give omega is 3 there, omega is still 3 there. So at any given time, I could find the velocity. Because I changed this cosine to sine, I would have to change this sine to cosine, and then this cosine to sine. So there's all kinds of things you can find out about motion just from looking at this one simple equation. And we're going to practice that lots and lots this unit. Okay, that's all for today, thinking mathematically about simple harmonic motion. I hope you have a great day, and remember, don't break the laws of physics.